To gain a non-conventional understanding of the nature and principles of ferromagnetism as a macroscopic phenomenon, we can turn to ring theory. Unlike standard quantum mechanical models, this theory makes it possible to construct models of atomic nuclei and electron shells as deterministically defined structures, allowing physical interactions to be described explicitly. A clear and explicit model of atomic structure is therefore essential for explaining the fundamental nature of ferromagnetism. As we outlined in previous presentations, the ring theory describes the atomic nucleus as a set of toroidal structures representing protons and neutrons. These structures are grouped into what are called globules, each formed from 2 to 5 pairs of protons and neutrons. The toroids symbolize regions where instantaneous electric charge values are distributed. In this way, the proposed nuclear structure directly influences the arrangement of electrons within the atomic shell model. The table shows schematically expressed models of the structures of the nuclei of atoms, of parts of the periodic table of elements. If we convert this graphical representation into a table according to the number of protons in globules, we can notice that there is a group of elements whose nuclear structure can be divided into 2 symmetrically separated halves. These elements include titanium, vanadium, chromium, manganese, iron, cobalt, and nickel. We classify them as ferromagnetic materials because of their ability to generate strong magnetic properties. In contrast, copper and zinc are excluded, since the arrangement of globules in their model nuclei cannot be divided into 2 symmetrically separated halves. According to ring theory, the model of the iron atom's nucleus is built from globules, each containing 4 or 5 proton-neutron pairs. The 2 central globules each consist of 4 proton-neutron pairs and are connected to one another through what we call a proton bridge. Each of these central globules has 1 free proton, to which a single 4s valence electron is bound. These bound valence electrons sit on opposite sides of the nuclear model, with opposing magnetic moments, and together they form the axis around which the entire atom can rotate. Attached to these central globules, in a symmetrical, alternating arrangement, are the terminal globules. These contain 3 or 4 free protons, to which the electrons of the second and third orbital shells are bound. The terminal globules are also connected via a proton bridge, but here an additional neutron is inserted between them to strengthen the bond and enhance the magnetic field between the globules. It's worth noting that the most abundant isotope of iron contains just 26 protons in its nucleus, but as many as 30 neutrons. In this model of the iron nucleus, the magnetic moments of protons and neutrons are arranged in a highly symmetrical configuration. In the upper region of the structure, the magnetic moments of the protons are oriented inward into the lobes, while in the lower region, their orientation is reversed, pointing outward from the lobes. When the magnetic induction lines generated by these protons are visualized, the magnetic field naturally separates into 2 distinct regions, whose magnetic fields repel each other. This mutual repulsion contributes to the dynamic balance of the entire nuclear structure. According to the proposed ring theory, the structure of the nucleus determines how electrons are distributed across their orbitals. This means that in the electron shell model of an iron atom, we can divide the electron arrangement of the second and third energy levels into 2 symmetrical halves. Before superposition, their magnetic field distributions form 2 distinct regions. After superposition, these regions dynamically repel each other and take on a directional orientation. In all ferromagnetic elements, and the iron atom is no exception. The two bonding electrons in the 4s subshell are positioned perpendicular to the axis that splits their magnetic fields into two repelling parts. These two valence electrons define the axis around which entire atoms are able to rotate. If you look at the 3 versus 4 atom model, the way the electrons are distributed is actually uneven and asymmetrical. This asymmetry is key because it causes the Haupt magnetic field to have an uneven directional intensity. It's this precise direction that allows atoms to bond at specific angles within the crystal lattice. In the case of iron, this is exactly what drives the formation of its body-centered cubic structure. To get a clear picture of how atoms are arranged and how magnetic fields point inside iron's crystal lattice, we can simplify the model. Instead of dealing with the complex fields between all the electrons, let's just picture two magnetic dipoles pointing in the same direction. These tiny basic magnets can rotate around an axis that's perpendicular to their plane. This axis connects two valence electrons, highlighted here in light blue, which form a covalent bond with neighbouring iron atoms along this line. In the iron crystal lattice, the atoms are arranged so that the axes of their bonding electrons are oriented perpendicular to one another in all three spatial directions. Atoms that are not directly connected through valence electrons interact instead through their own magnetic fields. Within planes perpendicular to the aligned valence electron axes, chains of atoms are formed by mutually aligned magnetic fields. These chains regularly alternate with neighbouring chains whose magnetic fields are oriented in the opposite direction. As a result, the overall magnetic field of the crystal lattice reaches a dynamically balanced minimum state through superposition. In the direction perpendicular to these magnetic chains, the individual chains are interconnected by covalent bonds formed by pairs of valence electrons from neighbouring atoms. When an external magnetic field, characterized by H out and B out, is applied, atoms whose valence electron axes are oriented perpendicular to the external field begin to rotate around the axis of their covalent bonds. As the system moves toward a new state of dynamic equilibrium, the original oppositely oriented atomic chains gradually break apart, while new chains aligned in the same direction begin to form. These newly created chains are oriented perpendicular to the original ones and generate a strong magnetic field within the crystal lattice in the direction of the applied external field. Regions of the crystal lattice containing these uniformly aligned magnetic chains are known as magnetic domains. Once formed, the atoms within these domains can remain aligned even after the external magnetic field is removed. However, if additional external energy increases the atomic motion beyond a critical level, the magnetic bonds within the newly formed chains can be disrupted. The atoms then return to their original arrangement, and the crystal lattice loses its magnetic orientation. Even atoms whose valence electron axes are not oriented perpendicular to the lines of magnetic induction of the external magnetic field are affected to some extent by the applied field. This makes it possible to meaningfully interpret and evaluate the magnetization curve, its characteristic parameters, as well as the processes of demagnetization, hysteresis, and other related magnetic phenomena. The formation of magnetic domains can be observed particularly well in iron nanostructures. Because of their extremely small size, typically between 1 and 100 nanometers, these structures often form a single magnetic domain and therefore display properties that differ significantly from those of bulk iron. Iron nanoparticles smaller than about 20 to 30 nanometers exhibit what is known as superparamagnetism. In this state, Each particle behaves as a single magnetic domain. When exposed to an external magnetic field, the particles become strongly magnetized, but once the field is removed, they retain virtually no residual magnetization or coercivity. Under the influence of an external magnetic field, not only do the magnetic moments of individual atoms rotate inside the particle, but the entire nanoparticle itself can also physically reorient in space. Cobalt crystallizes in a hexagonal crystal lattice. In this model, one half of the terminal globule contains 4 valence electrons, while the other half contains one globule with 4 valence electrons and a second globule with only 3 valence electrons. This asymmetry leads to an uneven distribution of the magnetic field generated by the electrons, which allows cobalt to form a crystal lattice with 120-degree angles within the hexagonal crystal structure. Nickel crystallizes in a cubic, face-centered crystalline lattice. His model of the nucleus and the electron shell is symmetrically divided into 2 magnetically repulsive parts. This regularity allows it to form a cubic, face-centered crystalline lattice. Other elements that also show ferromagnetic behavior include vanadium, chromium, and manganese. According to ring theory, these elements contain bonding electrons in the 4s sphere, located along the axis of the atomic model, while their electron shells are divided into 2 parts whose magnetic fields repel each other and remain in dynamic balance. Because these atoms contain fewer electrons than, for example, iron atoms, their overall magnetic fields are weaker than those of the best-known ferromagnetic materials. For this reason, their ferromagnetic properties are usually applied in combination with other elements or specific material structures. To explain the underlying principles of ferromagnetism as a macroscopic phenomenon in a non-conventional way, we have applied the foundations of ring theory. In contrast to standard quantum mechanical models, this theory allows us to construct deterministic models of atomic nuclei and electron shells, making it possible to explicitly describe the physical interactions involved. A clear description of atomic structure is therefore a key element in understanding the origin of ferromagnetism.